Okay, hi everyone, welcome back to this video series on cryptocurrency. Target representation. In example 10.3, we saw that the block contains the target in a notation called target bits or just bits, which in block 277316 has a value of 0x1903A30C. This notation expresses the proof of work target as a coefficient exponent format, with the first two hexadecimal digits for the exponent and the next 6 hex digits as the coefficient. In this block, therefore, the exponent of 0x19 and the coefficient is 0x03A30C. The formula to calculate the difficulty target from this representation is target coefficient hash 8 star exponent minus 3. Using this formula, the difficulty bits value 0x1903A30C, we get target 0x03A30C to 0x08 0x19 minus 0x03 target 0x03A30C 0x08 0x16 target 0x03A30C star 20xb0, which in decimal is target 238348 star 2176 target 228292029483939 92985074683310368 switching back to hexadecimal. This means that a valid block height of 277316 is one that the block header hash that is less than the target. In binary, that number must have more than 60 leading bits set to 0. With this level of difficulty, a single miner processing 1 trillion hashes per second, 1 terahash per second, or 1 th sec would only find a solution once every 8496 blocks, or once every 59 days on average. Retargeting to adjust difficulty. As we saw, the target determines the difficulty and therefore affects how long it takes to find a solution to the proof of work algorithm. This leads to obvious questions. Why is the difficulty adjustable? Who adjusts it and how? Bitcoin blocks are generated every 10 minutes on average. This is Bitcoin's heartbeat and underpins the frequency of currency issuance and the speed of transaction settlement. It has to remain constant not just over the short term, but over a period of many decades. Over this time, it is expected that computer power will continue to increase at a rapid pace. Furthermore, the number of participants in mining and the computers they use will also constantly change. To keep the block generation time at 10 minutes, the difficulty of mining must be adjusted to account for these changes. In fact, the proof of work target is a dynamic parameter that is periodically adjusted to meet a 10-minute block interval goal. In simple terms, the target is set so that the current mining power will result in a 10-minute block interval. How then is such an adjustment made in a completely decentralized network? Retargeting occurs automatically on every node independently. Every 2016 blocks, all nodes are retarget the proof of work. The equation for targeting measures the time it took to find at least 2016 blocks and compares that to the expected time of 160 minutes. 2016 blocks times the desired 10-minute block per interval. The ratio between the actual time span and the desired time span is calculated, and a proportionate adjustment up or down is made to the target. In simple terms, if the network is finding blocks faster than every 10 minutes, the difficulty increases, target decreases. If the block discovery is slower than expected, the difficulty decreases, target increases. The equation can be summarized as new target equals old target. Actual time of last 216 blocks, 2016 minutes. Example 1013 shows the code used in the Bitcoin Core client. Example 1013, retargeting the proof of work, calculate next work required in PCPP. The parameter interval 2016 blocks and the target time span 2 weeks as 1,209,600 seconds are defined in chain params.cpp to avoid extreme volatility in the difficulty, and the retargeting adjustment must be less than the factor of 4 per cycle. If the required target adjustment is greater than a factor of 4, it will be adjusted by a factor of 4 and not more. Any further adjustment will be accomplished in the next retargeting period because the imbalance will persist through the next 2016 blocks. Therefore, large discrepancies between hashing power and difficulty might take several 2016 block cycles to balance out. Note that the target is independent of the number of transactions or the value of transactions. This means that the amount of hashing power and therefore electricity expended to secure Bitcoin is also entirely independent of the number of transactions. Bitcoin can scale up, achieve broader adoption, and remain secure without any increase in hashing power from today's level. The increase in hashing power represents market forces as new miners enter the market to compete for the reward. As long as enough hashing power is under the control of miners acting honestly in pursuit of the reward, is it enough to prevent takeover attacks, and therefore it is enough to secure Bitcoin. The difficulty of mining is closely related to the cost of electricity and the exchange rate of Bitcoin vis-a-vis the currency used to pay for electricity. High performance mining systems are about as efficient as possible with the current generation of silicon fabrication, converting electricity into hashing computation at the highest rate possible. The primary influence on the mining market is the price of 1 kilowatt hour of electricity in Bitcoin, because that determines the profitability of mining and therefore the incentives to enter or exit the mining market. Successfully mining the block. As we saw earlier, Jing's node has constructed a candidate block and prepared it for mining. Jing has several hardware mining rigs with application-specific integrated circuits where hundreds of thousands of integrated circuits run the SHA-256 algorithm in parallel at incredible speeds. Many of these specialized machines are connected to his mining node over USB or local area network. Next, but the mining node running on Jing's desktop transmits the block header to his mining hardware, which starts starts testing trillions of nonces per second, almost 11 minutes after starting to mine block 277316. One of the hardware mining machines finds a solution and sends it back to the mining node. When inserted into the block, the nonce 924591 produces the block hash of. I'm not going to read all this, it would take too long on this. Immediately, Jing's mining node transmits the block to all its peers. They receive, validate, and then propagate the new block. As the block ripples out across the network, each node adds it to its own copy of the blockchain, extending it to a new height of 277316 blocks. As mining nodes receive and validate the block, they abandon their efforts to find a block at the same height and immediately start computing the next block in the chain using Jing's block as the parent. By building on top of Jing's newly discovered block, the other miners are essentially voting with their mining power and endorsing Jing's block and the chain it extends. In the next section, we'll look at the process each node uses to validate the block and select the longest chain, creating the consensus that forms the decentralized blockchain. So I'm going to leave it here today for this video. If you like listening, please consider like, sharing and subscribing. Thank you.